Hello, can you hear me?
Sir.
Yes.
All right, good. So let's start then. How are you doing?
Good.
Good. All right. So let's, what I'm going to do today, I'm going to first talk about the homeworks, how I solved the problem and the problems. And then we'll go to some new material, and it's the theme of today's lecture is spontaneous symmetry breaking, and it's an effect which has an extreme importance for our understanding how physics works, how things are, are working, and I'll try to emphasize that aspect, and I will also provide an example of simple example, something which we actually can calculate. Uh, of that phenomenon. But that's later. And now let me start with homework. So the first problem there was that you had Earth. Earth has radius, and it also was considered to be a uniform sphere, right? So it means that the density, mass density, is everywhere the same. Now you drill a hole here from one side to another, and the question was how, if you drop here some object, how much time it will take for the object to go to appear on the other end if you neglect all that dissipation, all air resistance, whatever you can. So what? First of all, as in every problem, you need to find you need to figure out what is your coordinate, right? And here's motion is one dimensional; it's just going straight line. So a good coordinate would be just a distance from the center, distance of the object from the center. The object here is the only thing which is moving, so we have only one coordinate. Let's call it coordinate x. So that when object is somewhere here, right, that object has some mass, and we know that the equation of motion. Everything is one dimensional, so we don't need to worry about vectors here. So an x double dot, right, the acceleration, m times a, equals the force which acts on this object. Now, the only force which acts on this object, because we neglected everything else, is a gravity. So we need to figure out what is the force here at the point where the object is its distance x from the center, and what is the force of the gravity. Well, there is Newton's law, right, of gravity. So F between two objects equals G m1 m2 divided by distance between the object squares. Let's use little fun. Right? That's Newton's law of gravity, and it works. So it's a little part. But you have to remember that it's not an equation which you can use anywhere, anytime. So it's a very specific situation. It's when you have 2 point-like masses, right? So they're point-like. It means that the size of each mass, the size of each object is much smaller than the distance between the objects. The distance between the objects is r. Each object can be thought of as a point-like object, and only then, if you have some other object, like some extended object, a point-like mass, right? And this object has mass m, and it has some distribution of mass inside it, and there is and this is object mass little m. Then the force between them will not be given by this formula, right? By this equation, because that equation is only for point-like mass. So what you need to do in this case, you need to take this object, split it on little pieces, right? Then you know the force from each piece, and then you sum up all the forces, right? So that's called integration, and you need to worry about vectors and so forth. So it's that sum up forces means sum up vectors, so forth. Then you can use this formula to compute the force between extended object and or between two extended objects. It really doesn't matter in this case until you start doing it. But even if you have one point-like object and the other is extended, you cannot think of it as a point-like object. Then you have to split it on point-like objects, and then you can use then you can use this formula. So this formula is definitely not applicable here, right? Because it's force is not point-like in this situation. That the distance between x is smaller than r. So we need to figure out what is what's the forces. We can do exactly the same procedure. We can split Earth on many small pieces and compute force between each of those pieces and our point-like mass using this formula, and then sum up all the forces and find the resulting force which acts on the object. It is actually doable. It's the integral which appears there can be taken, and it's not even very difficult. But it's not the easiest way to solve it. So the easiest way to solve it is to understand the following, what I try to emphasize all the time. The nature of the force doesn't matter, right? So it realizes that equation of motion, this equation of motion, does not care about the nature of the force. So if it were electrostatic force, that would be exactly the same equation, right? So we can, when you're dealing with forces, every force which looks the same would give you the same answer. And then what we can do is to compare this Newton's law with electrostatic law, right? Q1, Q2 divided by r squared. This is gravity, this is electrostatic. And you see that it's a simple change of notations. Right? Here is masses and here is charges. This is G, this is K, which is just number. So that gravity force behaves the same way as electrostatic force. And for electrostatic force, there is a Gauss law, which we can use. And Gauss law tells us that, the only force which we need to, what we need to do is to draw a Gauss surface, right? And the mass here will experience force, which is provided just what the material inside. And in this particular situation, for this particular problem, that the Gauss surface is a sphere, because the force is spherically symmetric and the problem is spherically symmetric, right? And the Gauss law is actually very difficult to apply in any other cases. And we will discuss it later when we discuss Gauss law in more detail. But that's here it's a standard situation. So the force which acts here equals G times M, the mass of the little object, right, times the mass inside this sphere, right? And that mass inside the sphere equals to the volume of the sphere, right? That's volume of the sphere. And you need to divide it by x squared. Right? That's the force due to Gauss law. That's the force which acts on that little mass F.
That's density.
Say again?
Times the density.
I'm sorry.
The volume times the density.
Oh, right. Yes, right. Yes, you're correct. Thank you. And so this is the force, and what we can see here, this is x squared, this is x cubed. So this is something proportional to x, right? X cubed, x squared, so it's some number times x. Well, but we know that when x equals r, the force must be mg. And we know when x equals 0, the force is equals mg, right? Because that means that object is right on top here, and we know the force here is mg. And at x equals 0, force equals 0. Equals 0. Right? And the function must be linear in x. So it means that the function must be mg divided by r times x. Right? That makes sense? That makes sense?
Yes.
Of course, you can do it differently, right? You can write that this is g m fourth third by rho. Then you write x here, right? Then you divide it divided by multiplied by r cubed divided by r squared divided by r, right? So what I did here is r cubed downstairs, r cubed in front, right? And then, but then this is the force which acts on it right on this surface. So on this surface it is mg. So what we have then is mg, which is exactly the same thing as this. Either way, it's it's linear in x function which has specific value here and here. So there is nothing else we can write. All right, so now it's not a complete story because although this is not vectors, they still have direction, right? It's a plus or minus. And now my x is up, going up. That's my coordinate. At this point, my force is going down, right? So it is minus, right? It has opposite direction. So what we have here is that this is minus mg divided by r times x. And well, what we see here is differential equation, and little mass cancels out. So x double dot equals minus g divided by r x. And you look at this, you see that this is oscillator, a simple harmonic oscillator. So that mass actually will be simply oscillate from top to bottom and then back. And the frequency of those oscillations are of course given by just this parameter. So it's square root of g divided by r. And then period of those oscillations equals 2 pi divided by omega, and this is r divided by g. Oh, sorry, 2 pi r divided by g and square root. Now the period is a full period. It's going there and back. We are not interested in that. We're interested only in going there and not going back. So the time which we're interested in would be half of that time. And then it's r divided by g. Okay, that's the answer. Now, at this point, it is very good to actually check units which you have, right? So what you have here, this is r. R is measured in meters. So let's call it meters. R divided by meter per second squared and square root, right? That's what we have. So what we see here is m meter cancels out and s squared goes on top. So this is equals second. The units, only units. I don't care about numbers. I only check units. So this is seconds, and that's exactly time units of time. So I get at least that part is correct, but it's also correct. All right. Any questions so far?
No.
All right. And the second part of this problem was to compare this time with the time that satellite is taken to go from all around. Well, again, it's a standard problem, and again, we know what the force acting on the satellite here, and this force is actually just mg, right? Right here, so it's mg, and it must be equal to mv squared over r. Right, so that satellite is going with velocity v, and that velocity v squared divided by r is its acceleration because it's a circle, and this is acceleration, this is mass. Acceleration times mass equals force. It's the same F equals ma. So what we have here is that velocity equals square root of rg. That's the velocity of the satellite, and the time which it takes to go from here to here is, of course, equals to pi r, distance divided by velocity, which is pi times velocity g goes down, and r divided by g squared. Right? So it is the same time going, right? That makes sense? That makes sense?
Yes.
All right. Now let me tell you a bit of about a few mistakes which were in homework. First of all, well, please check units of your answers at the end. If your units, if you have here time, means like seconds or whatever, minutes, hours, doesn't matter. The units of time on one side, the other side must also have units of time. And units can be computed just like just normal letters, like just normal algebra. If you have an equation where on the left hand side and the right hand side have different units, you definitely made a mistake. There is no other way to do that. There is no way that seconds can be equal to kilograms. It does not happen. It cannot happen. So it means, well, what it means is that you made some simple arithmetic mistake somewhere. So please then go back and recheck it. It's the easiest way to capture a mistake. You know, the difference between, say, me and you is not that I'm not making mistakes. I do a lot. But I usually capture them because I know all these tricks how to do that. So the first, I always check the units of every formula which I write on every step, actually, so that I know right away that if somewhere units do not match, I will know where to look at. So please do that. It's a simple exercise. You can do it like in less than a second, and it will save you a lot of grief and a lot of points in the homework on the exam. Right, that one mistake, and the other typical mistake. By the way, the other typical mistake is very common to engineers. You put numbers prematurely. You see that those two answers which I got are exactly the same. Right? Both of them have exactly the same answer. The time is exactly the same. And a lot of people, what they did is that they found that the first part, because it was said there, express it in problem, express it through R and G. But for the second one, they use that force as G m divided by R squared. And then did everything. And then substituted mass, well, that mass will cancel out. And then they substituted mass of the Earth, radius of the Earth, that G. And of course, you got different number. Because every two calculations will always give you, the same calculations will always give you a different number. Right? Because there is error bar. Error bars are knowing M, error bars are knowing G, error bars are knowing R. So you, in some cases, that's one point. And the other point is the computer which you use. I bet no one was calculating by hand. Or calculator also produces some mistake. Right? So you will always have some mistake in somewhere, like along, like in some place after a dot. But they're not real. I mean, it's not real differences between times. The time is given by the same formula. It must be the same. It's just numbers different because there is some error bar in every numerical calculation. So don't put numbers prematurely. If you want to compare one thing to another thing, express them through the same values and only then compare. Right? That's another thing which very common mistake. For some reason, students think that numbers are important, and well, they are, but they're not the most important part. All right, so that's one thing. Another thing is I want to, because I'm talking to engineers, that's the name of the class, right? I also want to say what is the difference between, at this particular example, what is the difference between engineers and physicists? So we calculated the time this way and the time that way, right? And that was, first of all, it was done for idealized problem. And there is always, of course, air resistance and all that stuff like in real situation. And it will change the answer, but okay, even without that, you see we're comparing time going from here to here and from here to here, right? And a physicists tend to say that the time is the same, right? But in engineering, if you try to think about it as a mode of transportation, then of course this time is shorter, right? Because this time requires you first to put the satellite up, right? Get it to speed. Then you go around, and then here you need to bring it down, right? Then the result will be the same. And it takes extra time, so it's actually not fair to comparison. And here, if you just drop an object, and again, if I neglect air resistance and everything else, with zero velocity, it will appear here with also zero velocity. It will be very easy to capture. But of course, the air resistance will change that. Right? That makes sense? Any questions?
No, sir.
All right. So next problem was just to repeat what I've done on the lecture.
Oh, wait, actually, I do have a question really quick, sir. We weren't supposed to consider the whole placing the satellite up and down in the question on the homework.
Right, yes. The correct answer is, of course, at the same time. I didn't ask you how much time it takes to bring a person, right, or whatever, goods. I said how much time it takes satellite to go from here to here. Right, so it's you did correct thing. What I'm trying to emphasize is that the reality is a little bit more complicated.
Okay.
Than the idealized problem. So it's and it's also difference between physicists and engineers. It's engineers actually usually better in those things because we tend to think that everything is like in reality it's not. Okay, so next problem is of course that the pendulum, and again what I noticed there that there were a lot of solutions which sort of repeat the equations which I wrote, obviously without thinking about it. And this is exactly what I wanted you to do, to understand how it all works. Because if I try to repeat things the way you write, the answer would not be the same as what you wrote. Right? So it means that you made a mistake somewhere and you didn't even capture it and you didn't recognize that it's a mistake. That's a bad habit. Come on, try to learn something of it. Try to learn how to deal with it. All right, so the first thing is to write a Lagrangian here. And so Lagrangian is our coordinate is of course this angle, and our Lagrangian then will be a function of velocity. Right? Theta dot. You see that dot here. It's important. And theta, the coordinate itself. This is a coordinate. This is velocity. Those are different, completely different things. They're not the same. It's in terms of Lagrangian, for the point of view of Lagrangian, those are completely different, independent variables. There is no dependence between this variable and this variable. For any when I write Lagrangian for any theta and theta dot, two different things, I can compute a number, right? So it's a function of two independent variables. This number is, of course, kinetic energy minus potential energy. Kinetic energy here, right? If this is the length of that pendulum L, is it L? Oh, I wrote that. Then it's velocity here. Velocity here is L theta dot, actually minus sign, and so it is velocity. You see, velocity. Velocity is how fast the coordinate is changing. So velocity is always derivative over time. right? That's how fast things change. So it's and then it's m over 2, right? Kinetic energy times the square of the velocity. So it's L squared theta dot here square, right? Now I need to write the potential energy, and if I measure it from here, then the potential energy is mgl 1 minus cosine theta, right? And what I have then is it's minus mgl 1 minus cosine theta. This is the potential energy. Just kinetic energy minus potential energy. Right? Does it make sense? It is a function of two independent variables. Please understand that that's important part of it. Those are two independent variables. So I treat theta dot and theta as completely independent from each other at this point. Right? So I wrote this function, and now I have this function, and those are two independent variables. Independent. It's important. Right? So now my Euler Lagrange equations are like this: the full derivative over time, partial derivative of L with respect to theta dot must be theta dot must be equal to dL partial derivative of L with respect to theta. You basically can check the units here. They also cancel out. Everything checked out. Is checked out. So now, when I take in this derivative, so let's write it dL over d theta dot, right? It's a partial derivative, theta dot. It's a partial derivative. So I treat theta dot and theta as completely independent variables. Theta dot is here. There is no theta dot here at all. It's a completely different independent variable. I must fix it and differentiate only with respect to this theta dot. So what I will have is ml squared theta dot, right? It's theta dot is its own letter. I just differentiate with respect to theta dot. That's all. It's actually simpler than what you think. Now I need to differentiate the L with respect to theta. Theta here is only in one place. It is here. This is not theta. This is theta dot. It's completely different, independent variable. So this is the only place where I have theta. So this derivative is minus cosine gives me another minus, so it's minus mgl sine theta. Okay. Now I need to place all of this in this equation. Right. So what will I have? D over dt. Now I just write it over there. That's it. ml squared theta dot. Right? Because that is dot here. There's no magical powers here. Nothing appears out of nothing. And it must be equal to minus mgl sine theta, right? Because that's what it is. Now, this is full derivative. That's specifically written as full derivative. It means that when I'm taking that derivative, now I remember that actually theta dot is a time derivative of theta. Only at this point I use it. I remember that. Right? So now when I differentiate with respect to time, those are constants. They do not depend on time, but theta does depend on time. It's already theta dot, so when I differentiate it, it becomes theta double dot, right? Because dot is exactly differentiation over time. So what I then have is ml squared theta double dot equals minus mgl sine theta. So theta double dot equals minus g divided by L sine theta. That's all. Right? That makes sense?
Yeah.
So you see that on different steps here, I treat that theta and theta dot differently. And that's why that the double dot appears here. What I've seen a lot, first of all, this equation was written without this dot. So it was written like this. In many cases. That does not make any sense whatsoever. Units are wrong here. You see that units of this one and units of this one are the same, right? Because it's the same expressions. But here I have 1 over time. I divide by time, right? So even units do not change in this equation. It cannot be right at all. Everything which has wrong unit, different units on left-hand side and right-hand side is definitely wrong. Simple like that. It's just very simple test. So that cannot be wrong. Moreover, if you try to do that here, you got nonsense. Okay? When people, that was one mistake. The other mistake was for somehow was written, the velocity was written like that, and then kinetic energy was written like this, without dot here. This is not the kinetic energy. There is no velocity here. Velocity is time derivative. Okay? So it's please just, you should understand that this is a very, very simple thing. They tell you what to do. You do exactly what is written. And that's it. If you got the wrong answer, it's something which doesn't make sense. It means that the procedure doesn't make sense. That's it. It doesn't mean that you're wrong. Okay? So please try not to invent things when you're doing it. You just do it what's written exactly. And if it says differentiate with respect to theta dot, you differentiate with respect to theta dot. And if your Lagrangian does not have theta dot, then it is 0. That's it. Okay? It really is very, very simple story. That's why we use it. I mean, it's because we don't like really complicated stuff. We always do simple stuff. All right, so that was the first part of the problem. And the second was to do the Newtonian mechanics. Well, Newtonian mechanics, you have here mg, right? And your motion only along this circle of radius L, right? So you take this mg and you find what is its projection on the direction which is tangential to this circle at this point. Right? Well, you can do it differently. You can use angular momentum and torque, or this way. It really doesn't matter. So that projection here is mg sine theta. That's this projection. Because this is this angle with theta, right? So this is 90 minus theta. So the cosine of the 90 minus theta is sine theta. Now, if this is your theta, then that force it brings it in the opposite direction than theta, than growth of theta, right? So it minus sign, and now we have here the acceleration. The acceleration is m l theta double dot, right? The acceleration as velocity is l theta dot, and acceleration is just one more dot. That's all. And so this is your acceleration, and so what we have from here is theta double dot equals minus g divided by l, which is the same equation as this one, of course. All right? Does it make sense?
Yes.
And another thing is, guys, please never write it to me that of course it will be the same. And that's it, without any calculation. Because my question will be, how do you know? And the answer, because we were told so, is wrong answer. You need to compute it and show. Otherwise, it's not an answer. I'm not here to indoctrinate you, right? Everything which I say must be taken. Well, I try not to lie, okay? And I don't. But what if I made a mistake? What if something is wrong with the procedure? The idea is for you to check it and to see that it actually does work and how it is, how it works and so forth. So it's actually that's the reason. You always need to doubt, and you always have to doubt is when what you're told. I'm not some kind of prophet. All right. So let's then start now our. Any questions about the homework? No.
No.
All right. Okay, so let's start with the new material. And what I want to show you is kind of surprising. It's usually it's when I give sometimes public lectures, it's always surprises people. So think about it the following way. All our laws of physics are what is called translational invariant, right? What it means is that all laws of physics here are exactly the same as all laws of physics over here, right? Otherwise, we wouldn't know. We wouldn't be able to formulate. If all our laws of physics depend on where we are, then well, we would give up right away, right? Because well, how you deal with that? If you need to know precisely where you are with respect to what, by the way, if you're to formulate it. No, all laws of physics are exactly the same everywhere, right? That makes sense?
Yes.
Okay. Now, here's a question: how comes this wall exists? If all laws of physics are the same, and I can walk here, then how come I cannot walk through this wall? Can you answer this? Everything must be the same, right? All the laws of physics are the same. How come there is a rigid object and not rigid object? That the universe must, if you take it for as it is, then the universe must be either be one whole rigid thingy, right, where nothing can move, or it must be like it must be uniform, right? All the laws of physics are the same. How comes the properties of the universe are different in different points? There is a wall in some point, there is no wall in the other point. There is a desk here, there is no desk here. It should be either all desk or no desk at all. Because all the laws of physics are the same, and everything is obeying laws of physics. Right? You cannot violate laws of physics. Can you answer this question? Come on. I need to.
It's because I would assume the charges within the body kind of repel your charges in the body.
Yes, of course. How comes they repel here and not repel over here?
There's no charges present, or there's no
Why
like.
not? That's exactly the question. Why not? If all laws of physics are the same, how come there are places where there is charge and there's places where there is no charge?
There's different strengths of forces at different points in space.
So, no. Coulomb's law is exactly the same everywhere.
No, I meant like there's more accumulation of charge in one place compared.
That's exactly my question. Why do they accumulate there and do not accumulate over here? Why there is at all any non-uniformity to begin with? All laws of physics are the same, so there is no point, there is no reason for them to accumulate in one point and not accumulate to another. Right?
Yeah.
So, but you're of course right that something is wrong here, right? Well, we do have a wall, and physics does work. And so, what is it all? But how? What's going on? And it's I can give you another example of the same kind. Let's say that we have a table, right, or desk, and it's completely horizontal, and we have a very completely vertical rod, and we put pressure on top. So there is a piston which applies huge pressure. Exactly vertical, so everything is exactly symmetric with respect to that axis. Right? That makes sense?
Yeah.
And we apply more and more pressure on it. What will happen? If it's
At
like,
a,
go ahead.
at a certain point, like you're going to exceed like the stress of the pole or the stick that you would have, and it couldn't handle that much more force.
And what will happen?
It'll break.
Well, it will actually not. If you, well, now it depends. So let me specify a little bit more. That rod is long and very narrow.
Is it a rigid body?
Yeah, it is. But it's long. But just imagine that you have long piece of rod and you try to squeeze it. What will happen?
And I assume the body that's on top of it would always be vertical, like it wouldn't have any sort of like.
Absolutely, everything is very symmetric. It's just going like this. With it. What will happen, just from your experience?
Like you would exceed a certain point that it couldn't handle that much pressure anymore, and it would like collapse on itself, or it wouldn't necessarily snap, but it could.
Okay.
It would bend.
What? Say it again.
It would bend.
Exactly, it will buckle, right? It will buckle. Where? I mean, to what direction? We understand that it will buckle in the middle somewhere, but to what direction? This direction, or this direction, or this direction, or towards the blackboard? Which direction will it buckle?
It actually depends solely on like, I guess, the makeup of the material. Kind of like even if it was uniform. No, if it was uniform, then it wouldn't. I guess it's by chance.
Exactly. That's the correct answer. That's the correct answer, simply because it's unpredictable. If you have completely uniform system with completely symmetric applying forces, everything is completely symmetric with respect to the vertical line, then what will happen is that there is noise here, right? I mean, there's air around, and it hits it, and those little hits will decide eventually which way it buckles, because any small noise will make a decisive role here. No matter how small it is, it will eventually provide you with some direction of the buckling, and it's completely random. Okay? So you see that everything was absolutely symmetric, and if you consider noise, it was also actually symmetric, but it's noise, right? So it fluctuates a little bit. So those fluctuations, for some reason, at some point, when the squeeze is towards that buckling point, right? Very close to the buckling point, that noise becomes very important. It's completely not important anywhere else. Well, it's a small noise, it doesn't really matter, you just squeeze it in there. But at some point where it's about to buckle, that the role of the noise becomes very important. Right? And that's exactly what breaks the symmetry. You see, before, right? When we start to squeeze it, it was absolutely symmetric system with respect to the. I'm sorry, there's some noise. Do something about it. So the system was absolutely symmetric with respect to vertical line, right? And at some point, that symmetry is broken. Although the symmetry of the state is broken, right? The rod was initially very symmetric. Everything which we put on it is absolutely symmetric with respect to this. But the state of the rod, its shape, in this case, is not symmetric. So that symmetry is broken spontaneously. It's broken by some noises, some smelly, extremely small fluctuations, right? So You see that and that's exactly what happens with that collection of charge somewhere, right? Because what will happen if you assume that the universe is completely uniform, right? And like there is only Coulomb forces, forget about everything else, and there is some fluctuations which increase, very very small fluctuations, but that's enough. It will increase volume, it will increase density of charge somewhere. That charge will start to act a lot stronger, not a lot, just a little bit stronger, but it will break the translational symmetry. Okay, that makes sense.
Yes.
So there is that system which are there are situations where we call what we call the spontaneous symmetry breaking, and that effect that it has been studied quite a lot, and some of the classic works of that on the theory of those of such transitions have been done by my colleague who is like doors next door to my office, Valery Pokrovsky, and. So it's all called by spontaneous symmetry breaking, but it's responsible. It's the main effect in many different stories, like Landau's theory of phase transitions, for example, second order phase transitions. That's the main story there. I don't know if you heard about Higgs boson. Higgs boson is exactly what condensation. They say condensation of Higgs boson. That's exactly the same story. Superconductivity, superfluidity, magnetism, right? You know that if you increase temperature, the magnet will lose its magnetization. When you decrease temperature, the magnetization will appear again. Now you can make magnets which are completely isotropic, so there is no specific directions inside that, and still the magnetization will appear somewhere. It will pick its direction, right? And then the whole magnetization. By chance, it will pick direction by chance, and then it will appear. So that sort of by chance breaking of symmetry is what we call the spontaneous symmetry breaking, and it's very 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 universal story. It's the same everywhere. It's the same for Higgs boson. It's the same for magnet. It's the same for here, and so forth. Machinery is completely different. And in one case, you have to use quantum field theory. Here is just simple, well, not very simple, but it's elasticity theory and so forth. But there are some very very universal features of that, and that's exactly what I'm going to discuss. That universal features of that spontaneous symmetry breaking. Again, I want to emphasize that this is probably the most important feature of physics. That's why we exist, despite the fact that all our laws, all physics laws, are completely uniform. Nevertheless, we do exist, right? Their molecules exist, Earth exists, people exist, and so forth. Without that mechanism, that wouldn't be possible. So, the main story of that mechanism is the following: that if you have an equation, right, some law of physics, which has some symmetry, like translational symmetry, rotational symmetry, right? That symmetry rotation about the z-axis, and so forth. You have all the equations which are absolutely symmetric with some symmetry. The solution of that equation does not have to be symmetric with respect to the same action. And that's exactly the reason why we have such phenomena. So in order to illustrate it, I want to solve some simple problem, some mechanical problem, which actually illustrates that. And the problem which I want to solve is the following. Let's consider a hoop which is rotating, which is staying vertically like this, right? And it rotates around the axis, the vertical axis, with some angular frequency omega. Okay? Now, on that hoop, there is a beam which can move around without any friction on the hoop. Okay? That makes sense?
Yes.
So imagine that I have a hoop, right? I stay in vertical plane, right? And then I take that vertical axis of the hoop, and I start to spin that hoop around that vertical axis. And on addition to that hoop, I also have a bead on a hoop which can move around anywhere without any friction very easily. But it can stay, but it must stay, of course, on the hoop. Okay. So that's the problem which I want to consider. And what I will claim, well, the claim is that when omega becomes large enough, that something new appears, something interesting. Now, what is interesting for me as a physicist, or what we as physicists consider to be interesting? You see that I really don't care about that hoop and that bead. But really, I mean, I have no use for this problem except maybe giving to students as homework. And what's interesting to me, and some effects which I can study on a simple system, but which I can then use in studying more complicated ones. That sort of idea of universality, that there are some mechanisms in physics which are universal. I can study them on simple systems, understand everything about those mechanisms, and then use them on more complicated systems, where I cannot do all the calculations, but I still can guess the result. That's called intuition, right? So that's exactly what we're always aiming at. Trust me, no physicist is interested in how far the ball or the cannonball will fly if you shoot it with 5 meters per second initial velocity at the angle of 39 degrees. I mean, it's such an interesting question. It's really, I mean, it's a boring stuff, right? The interesting stuff is if there is something which I can learn about that problem, which I can use somewhere else. And shooting cannons is not really something which we can use to learn something else, but this is. And I want to illustrate this effect of spontaneous symmetry breaking on this simple system, which I can solve. Right? That makes sense?
Yeah.
All right. So let's solve it. And we need to write equation of motion here. And for that, of course, we need to first figure out what our coordinates are. And at this point already, there is a subtle moment. And the subtle moment is the following. What is that omega? And in this particular problem, which I want to consider, that omega is given frequency. So there is a motor here, which rotates it with a given frequency, always. Right? So that frequency does not change no matter what. I can change it. I have full control over that omega. But the system itself cannot change it. This is very different from the story if I just spin it once and let it go. All right? Then that frequency of rotation would depend on where is that bead is. Because total angular momentum must be conserved, right? And when the bead is going up or down, the moment of inertia is changing, and then the frequency would change. So at this, if I had such problem, then I needed to introduce two variables: the rotation of the hoop, it has its own angle, and the position of the bead. Right? Does that make sense?
Yes.
So this is theta, but now what I have is that instead, right? I have a motor which keeps it rotating with some fixed frequency. It means that I always know what angle I have rotated, right? I just multiplied omega by time. I know what angle I have rotated. That's the hoop. So there is no freedom. There is no degree of freedom in the rotation of hoop. It means that I do not need to write an equation for the rotation of the hoop itself. The only equation which I need to write is for the motion of the bead. Right? So let's call it the mass m of the bead and radius r of the hoop. And then the only degree of freedom which I have in this problem is that angle theta. And so that will be my my coordinate, my generalized coordinate. Does that make sense?
Yes.
You see the difference between the two problems, right? one is the forced motion with fixed omega, and the other is just spinning it once and let it do whatever it wants. Those are two different problems, and they have different solutions. All right, so I have that omega is fixed, and all I need to do now is to write Lagrangian, of course. Well, I can do it with forces, but I don't like forces. So it's I'll do it with Lagrangian. So again, Lagrangian here is a function of two variables, theta and theta dot, right? So and it's kinetic energy plus minus potential energy. So I just need to write. Well, let's first write what is the potential energy. Well, the potential energy is exactly the same as for the pendulum. So it's mgr 1 minus cosine theta. That's my potential energy, right? Because it's the same as pendulum. It's just moving around the circle, right? Radius arm. But now I need to write kinetic energy of it. And so the kinetic energy is mv squared, right? So the kinetic energy is mv squared over 2. V is the vector, right? So that velocity of that mass, of that beam, has two components. One of that along the hoop, right? And that component equals r theta dot. Let's call it that component v theta, and it equals r theta dot. Right? That makes sense?
Yes.
But there is another component which is right in the desk, right in the blackboard. Right? At this particular moment, it is right in the blackboard. So let's call it v omega. Right? And that velocity equals omega times this distance. And this distance is r times cosine theta. Right? That makes sense?
Yes.
No, it doesn't, because it's sine theta. So this length is r times sine of this angle, right? Right? But now notice that those two components are perpendicular to each other. This component, v theta, is in the plane of blackboard, and this component is perpendicular to the plane of the board. So those two components are perpendicular to each other. So it means that the total kinetic velocity squared is just the square of one component plus square of the other component. So it is r squared theta dot squared plus this component, omega squared r squared sine squared theta. Right? And this is velocity because omega is 1/2, right? It has units of the velocity. That make sense?
Yes.
So now my Lagrangian is kinetic energy mr squared theta dot squared dot, here dot you see, divided by 2 plus m over 2 omega squared r squared sine squared theta minus mgr 1 minus cosine theta. That makes sense so far?
Yeah.
This is my Lagrangian. And now I know what to do, right? I need to write Lagrangian equations and so forth. But remember, that's not, I don't want to really solve this problem. I want to see something about this problem. So let me now look at this Lagrangian. And first of all, see where is this variable, theta dot and theta, right? So the theta dot is here. And nowhere else. There is no other theta dot anywhere. Right? Everywhere else, I have only theta. I have theta here. and I have theta here. Right? That makes sense?
Yes.
So now when I take the derivatives of Lagrangian, I take derivative of theta dot with this term and the rest, all this rest of it. I must take the derivative with respect to theta. And but now let me do it differently. Let me now remember that Lagrangian defines my problem. That if I know a Lagrangian for my problem, I know everything about it. Right? I can write equations of motion, solve them, and find the solution. Right? All information about my system, mechanical system, is contained inside Lagrange. That makes sense?
Yeah.
But then if I have a Lagrangian in front of me, I don't really care where it comes from. Right? I have a Lagrangian, I know what to do. I know how to write equations of motion. That's it. So I look at this Lagrangian, and I say, well, let's imagine that I'm really solving different problem. That this is my kinetic energy, and this is my effective potential energy with minus 10. If I had a problem like that, where kinetic energy is just this term, and my potential, effective potential energy, I will call it. It's not real potential energy. Real potential energy is just this one. Just this one. But I sort of say that if I consider different problem with kinetic energy given by this term and potential energy, it's just this one. It's minus m omega squared divided by 2 and r squared sine squared theta plus mgr 1 minus cosine theta. If I had a problem which this kinetic energy, and this is kinetic energy because it has velocity in it, and the potential energy is given just by this, by such function, which is just a function of variable theta, one variable, right? So if I had a problem with this kinetic energy and this potential energy, it would have given me exactly the same Lagrangian, right? Does that make sense?
Yes.
So it means that if I had such a problem, then all my equations of motion, because Lagrangians are the same, equations of motion will be the same, solutions of the equations of motion will be the same. So instead of my original problem, I actually can study some artificial problem where this is my effective potential energy. So from now on, I just treat this as kinetic energy, this is as effective potential energy. That's all. Now my Lagrangian has a very simple form, right? It's m r squared over 2 theta dot squared minus u effective of theta. And my Lagrangian equations of motion are also very simple, because now it's exactly the same as we have done for the pendulum. If I need to take this Lagrangian, I need to differentiate it with respect to theta dot. Theta dot is only here. I differentiate it with respect to theta dot. I got m r squared theta dot. Right? That's the derivative of that with respect to theta dot. Right? Theta dot is only here. Now I need to differentiate it with respect to time. Remember Lagrange equation: d over dt, dl over dt theta dot. So when I differentiate with respect to time, all I do is just to have another derivative here, because everything else is constant. And it equals to minus. Now I need to take this Lagrangian, differentiate with respect to theta. Theta is only here. There is no theta here. It's theta dot. So it's theta. So it's u effective divided by d theta. Right? That's my equation of motion. And that's known function, right? This is just written here explicitly. So all I need to do is to differentiate with respect to theta. Does that make sense?
Yes.
Okay. So, well, first of all, we noticed that this is one-dimensional motion, our standard one-dimensional motion in some potential field. Right? This is my potential. This is potential. This is standard kinetic energy. The standard is call this mass. This is acceleration, and acceleration equals velocity equals force. Right. So but we already solved every one-dimensional problem of this form. Remember the integral representation, blah blah blah. So we actually can write the exact solution of this problem here. That's not what I want to do. I want to figure out what's happening here. And so instead of doing that, what I want to see is where are the equilibrium points? Where are the points where force equals 0? My effective force. The effective force is du effective divided over d theta, right? That's the force for this problem of that new problem. What would have called a force? Force is ma, right? This is ma. This is force. So let me take this derivative of this equation, du effective over d theta equals, now I just take the derivative, right? This is sine squared, so it's minus m omega squared divided, well, 2 is cancels out, so it's m omega squared r squared, m omega squared r squared, cosine theta, sine theta. And this is the derivative of sine squared. And plus, now I need to take this derivative. I have minus sine here. This is plus sine here, minus sine. Differentiate cosine get minus. So it's m gr times sine theta. Okay. So now let me write it the following way. This is mgr. This is cosine theta, and then I have minus mgr, and this is sine theta. It's the same expression. I just pulled sine out, and I also can pull m out and one of r out. So let me do that to simplify it. So I'll have g here, and I have m here, and r, and here I have minus mr. Right? That makes sense?
Yes.
All right. Now remember that I want to find what is the equilibrium points are. Equilibrium points are the minimum or maximum of stable or unstable equilibrium. Equilibrium points are the minimum or maximum of potential energy. Or in other words, it's the points where there is no force acting on my system. So that what it means is that I need to solve equation when du effective over d theta equals 0, right? Because this is force, right? So it's minus force. So if it equals, it's the same thing, right? It's either minimum maximum of effective energy, or those are the points where the force equals 0.
So split into two solutions, right? With the sine of theta and the cos.
Yes, very good, very good. But we need to analyze it a little better than that. But that's very good. So let me write it somewhere. So there are two solutions, right, of this equation. So if I want to say this equation, one solution is when sine equals 0, and those are actually two solutions. Theta equals either 0 or pi. Okay, that's one solution, and the other solution is given by this when this equals to 0. That's actually why I wrote it this form in this expression in this form. So when this equals 0, it means that cosine theta equals g divided by omega squared r. G divided by omega squared r. I don't know, can you see this? Small. And G divided by omega squared R. That makes sense?
Yes.
All right, so let's look at our at our system and see where those points are. And so let's first, with blue line, I will draw this point. So theta equals 0 and theta equals pi. So this is 0 and this is pi. Those 2 points, right? That makes sense? Right? That's what there.
Yes.
Now let's look at those 2 points. Where they are. And now, if you look at this is an equation. Okay, let me write it here. And then I wipe it out. So, cosine theta equals G divided by omega squared R. Now, but remember, omega is my parameter which I control. So I can make it large, I can make it small. So what will happen if omega is small?
It'll be wanting to go towards like the value of gravity or the acceleration due to gravity.
Omega is small. Think about it in this equation. Then what is this? It's large, right?
Yeah.
But it's cosine. It cannot be large. It cannot be larger than 1. Right?
Yeah.
So it means that if omega is larger, no, smaller than G divided by R square root, right? So omega squared, this omega squared here, is smaller than G divided by R. This equation does not have a solution. Okay? Simple like that. And there is no extra point. But if omega is larger than G divided by R, well, then it does have a solution. Okay? So let me, instead of writing G square root of G divided by R, let me call this omega critical. It's a critical value of this omega, G divided by R square root. By definition, so it's definition of critical omega in this particular case. So when omega, then what I have here is there is in this problem there is special critical omega. By the way, you may notice that it's exactly the frequency of the oscillator. Omega critical, so that when omega is less than omega critical, this equation does not have a solution. When omega larger than omega critical, that equation does have a solution. And this that equation through omega critical is written in a specifically simple form, that this is omega critical divided by omega squared, right? G divided by R square root is omega critical, so this is omega critical squared. So let's see how it actually happens. That doesn't make sense so far?
Yeah.
So let's see how it actually happens. And okay. Remember that if we have a unit circle, the cosine of this angle is just this length, right? Right?
Yes.
So let me draw the line which corresponds to the right hand side of this equation. Now, if omega less than omega critical, then what I will have is a line somewhere here, right? When omega is less than omega critical, this number is larger than 1. Omega is less than omega. So this right hand side is some number here, some line here. Now if I increase omega, when omega critical omega equals omega critical, then this is 1, and my line is exactly here. And if I increase it even more, then my line goes here, right? And my solutions then is exactly those 2 points, right? Because the cosine of those 2 points equals exactly my omega critical divided by omega. Does that make sense?
Yes.
So when omega is larger than omega critical, but not too large. I mean, I'm not interested in what's going on over here. I will consider only omega close to omega critical, but a little bit larger. So when those 2 points are, when omega just a bit larger than omega critical, what I have is those 2 points appear here. New solutions, new equilibrium points appear here. Right? So they first, when I cross, if I very, very slowly increase omega, right, they first I don't have those solutions. Then when I cross omega critical, they will appear first at very, very small angles. And if I increase omega more and more, they will start to move out. Does that make sense?
Yes.
All right, so let me use the same thing here and write it as omega critical divided by omega squared. And that solution only exists if omega larger than omega critical. Okay? Now we still need to understand what is stable solution, what is unstable solution. Which one of them stable, which one of them unstable. So let's first consider omega less than omega critical, small velocity, right? Small omegas. Well, let's consider just the smallest one of them. Let's say that it's 0. Then we know exactly what happens, right? This is unstable. And this one is stable. That makes sense? Do you understand this?
Yes.
Yeah, all right, good. So when omega is very small, it's like omega is that omega is almost 0. And then we know the solution. Like, I mean, it's intuitively clear. Of course, you can compute all of that from the second derivative, and I just don't want to. And because I think it's clear. But now what happens when omega becomes a little bit larger? Well, the picture stays the same. But what happens when omega becomes equal to omega critical? Or a little bit larger than omega critical? When it is a little bit larger than omega critical, we have equilibrium point here, equilibrium point here, equilibrium point here, equilibrium point here, right? But remember, it's a one-dimensional problem, and any one-dimensional for one-dimensional function, right? Omega u effective as function of theta. It can only have maximum, then minimum, then maximum, then minimum, then maximum, then minimum, right? You cannot have 2 maximum in a row. There must be a minimum in between them. That makes sense?
Yeah.
So this one is always unstable. So it is the maximum of our potential energy. But then next to it must be stable. The next one. So this has become stable. But then this one is unstable because after minimum must be maximum. So this point becomes unstable. And then this one is stable again. Right? That makes sense? That makes sense or not?
Wait, which case would it, the the one at the bottom be unstable or following the pattern of stable, unstable,
When
stable?
omega, look, as soon as those 2 points appear, this is unstable, right? So the next one must be stable.
Yes.
Because after maximum must be minimum, right? So it means that as soon as this point appears, it means that omega larger than omega critical. But as soon as it appears, it becomes stable. This is unstable. The next one must be stable. But then the next one must be unstable.
Yeah. Okay. I just wanted to make sure which case we were.
So as soon as those 2 points, red points, appear, the very bottom one becomes unstable.
Yeah. Okay.
But now think about it. What happens in this case? First of all, we look at our effective potential energy. I'm sorry that it's written crumbled here, but here's my effective potential energy, right? So notice that I change theta to minus theta. Then sine changes sine, right? Sine of theta becomes minus sine of theta. Right? If I change in this equation, I change theta to minus theta. Then sine theta becomes minus sine theta. Right?
Yes.
Okay. But it's squared here. So when I change theta to minus theta, this term does not change. And this term does not change. Here's cosine. When theta changes sine, theta goes from theta to minus theta. That cosine does not change. Cosine is even function. Right? So this term also doesn't change. So this potential energy has a symmetry. If I change theta to minus theta, potential energy does not change. It's symmetric. It's even function of theta. That makes sense?
Yes.
Okay. But now think about it. Let's imagine that I started my system. My bead is at the bottom. And let's include a little bit of dissipation. Otherwise, it's difficult to have an equation. Now, let's imagine that I start to increase omega. And I increase it through omega critical. Then this point becomes unstable. Right? So the bead should go either to this one or to this one. Right? But notice that again, let me just repeat it. My potential energy is always symmetric. Doesn't matter what omega is. Nothing changes with that symmetry when I go through omega critical. It is still a symmetric function. Okay? That makes sense?
Yes.
But my state, which I observe, my bead will be either here or here. Either or, it cannot be in the two places at once. So it will be either one side or another side. So the symmetry would be broken. The only non-broken symmetry, the only places where symmetry is not broken is when bead is right here or right here, right? Then theta to minus theta, when theta is 0, is the same point. But here, when I change, if in this state I change theta to minus theta, it's as if my bead moved from one point to another. So that's exactly what I'm trying to illustrate. That you see that my theory, my potential energy, my Lagrangian, my potential energy is symmetric when I change theta to minus theta. I have a symmetry in the problem. But the state which I observe, the bead is either on one side or another. Right?
Yeah.
Makes sense?
Correct. Yeah.
So the state breaks the symmetry of the problem. The equilibrium state breaks the symmetry of the problem. The problem is still symmetric, but the state which we observe is not. Okay? So let's consider it in a little bit more detail. The effect is happening right here, right when omega is very close to omega critical, right? That's the only point which is interesting. At this, when omega is very close to omega critical, that equilibrium points are very close to zero. They start from here, right? And they move right from zero, and they move to the other side. So when omega very close to omega critical, my theta is small. Equilibrium position, right? So then what I want to do then, I want to write my effective potential energy. I want to write my effective potential energy, this effective potential energy, when theta is much smaller than, let's say, 1. So theta is very small, and omega is very close to omega critical. So omega very close to omega critical, it means simply that omega minus omega critical absolute value much smaller than omega critical, right? So the difference between two frequencies is much smaller than the frequency itself. That means that it is small. So in this case, I can actually simplify my effective potential energy, and that calculation is done in my notes, but I will just write the answer here because I'm already running out of time. And the effective potential energy at those conditions when theta is very small. So theta is very small, theta is very small, and omega minus omega critical is much less than omega critical. Then my potential energy will have using Taylor expansion, and again it's done in my notes. What I will have is U effective of theta is approximately this way. There's some constant in front. I'll skip it. This is mr squared omega critical minus omega times theta squared plus 3 divided by 4 factorial. This is just next order term in Taylor expansion, and it's mr squared omega critical squared theta to the 4th. Okay, that makes sense? So I just took this expression and I use the Taylor expansion up to theta to the 4th. And there are some other terms, but they're small. They're not important. The two important terms are here. Now there is big reason why it is theta to the 4th. Why do I need it up to the 4th term? I will skip that reasoning here. Just but you can figure out yourself. So now let's see what actually happens here. First of all, we still see that when I change theta to minus theta, nothing is changing because it's only even powers here, right? So my potential energy is still symmetric when I change theta to minus theta. But what happens when omega becomes larger than omega critical? This term changes sign. The square term changes sign. Okay? That makes sense?
Yeah.
So let's see how it looks like. Let's draw. Remember, I told you always draw the potential energy function. So let's draw it. So this is my effective potential. Right? And let me first draw it when omega is less than omega critical. When omega is less than omega critical, this term is positive, right? And what I have is square, and then with positive coefficient, and fourth order term. When theta is very, very, very small, right? This term is much larger than this one. Because theta is small, theta to the 4th power is less than theta to the 2nd power. So when theta is very small, what I have is this. And of course, I messed up this. Okay. Well, it's this. Right? It's just a parabola. Nothing else. And then it just goes up, and that's it. When theta goes to, when theta becomes larger and larger, it goes larger and larger. So it's monotonically goes like this. So this is this case. Now let's consider a situation when omega is larger than omega critical. Then this is negative. And again, when theta is very, very, very small, I can neglect this term in comparison to this one. But now it's still a parabola, but that parabola has negative coefficient. So it goes down, right? Its horns go down. So I have this one. But now, after that, when theta becomes larger and larger, this term becomes dominant. Because when number is large, number to the fourth power is larger than number of second power. But coefficient here is positive, right? So that it means that the function must increase. So it must have some minimum somewhere and go like this. Okay? That makes sense?
Yeah.
So now you see that all that equilibrium which I drew before, theta equals pi is out of the picture because this is only for small theta. Right? So theta equals pi we lost, but it's vegetable. It does nothing. When omega is small, I have that blue line, right? Then this is my equilibrium point. But when theta becomes larger than omega critical, then this is my two equilibrium point. Right? That makes sense? That makes sense?
Yes.
All right. So next thing, and this is how it always happens. This is very, very universal form. There is pretty much nothing else you can write. Because for small theta, any potential energy for small, close to equilibrium, right, must have some form like that. It must be square term, force term, and so forth. If you have the symmetry theta to minus theta, you only have even powers at your disposal. So it will always have something like that. And then transitions, the symmetry break in transition, right, happens when the coefficient in front of the quadratic term changes sign. So when coefficient in front of the quadratic term changes sign, instead of blue line, blue potential energy, you got red potential energy, and your equilibria are here, right? And you either in one or another. So your state will break the symmetry. That's what I draw here is called the Landau theory of second order phase transitions. And but that's how it happens. All the superconductivity, Higgs boson, magnetization, everything has exactly the same form. It's not energy, it's a free energy there, and instead of omega, it's a temperature. And how to get it is more complicated story. But nevertheless, the mechanism itself is exactly that. That the transition temperature, Tc, or what the transition temperature for the magnet, when the coefficient in front of the square of your order parameter changes sign. In order parameter is magnetization, and when you have magnetic transition, it's some phase when you have superconducting or Higgs, whatever. So it's a variable which you use to describe your system. So if you have some variable which describes the system and your system is symmetric, for example, but symmetry can be different, but this is the simplest possible one. When theta to minus theta, that's symmetry. When coefficient in front of the square changes sign, you will have the transition. And that transition is very, very universal because it happens exactly the same way all the time. In particular, after that we can, and I do it in my lecture notes, but I need to wrap up, whatever, I need to finish. And so let me just say what some answers are. So after we've done that, we can actually consider small oscillations about those minima. Either this one or this one. And they are different. the frequency of small oscillations will be different in both of them. Right? Not very much different, but by square root of 2 actually, the difference. But what it means is the following. Like think about it. That if I have those hoops, but they're very, very, very small, so I cannot observe them, right? But let's imagine now that beads are charged particles. Then what I can do, I can actually shine light on it, on the system, right? And because charged particles interacts with light, if my frequency of my light corresponds to the frequency of oscillations, I will have a resonant absorption. Right? My light will be absorbed quite strongly because I'm at resonance. So this way I can actually measure the resonance frequency even of small oscillations, even if I don't see that. Right? If it's those hoops are very, very small. Right? But then if I go through transition and instead of one minimum I have to another, I will measure the change of the frequency of oscillation. And so I can actually see that the transition is happening. Moreover, if I have some dissipation, I always have dissipation, right? Then the width of the resonance will be different in different cases. And then I will actually know. But remember that width comes from dissipation. Dissipation comes from coupling to some larger system, which I actually don't even know to begin with. So just measuring the width of the resonances, I actually can learn something about the system which I don't know. Right? So that's one of the tools how we learn about materials when we don't know everything precisely. We just measure the properties of the resonance. But in this case, I actually can see that transition is happening. Right? So one more point which I want to make, and let's draw the graph omega, and here I have my theta of equilibrium, of stable equilibrium, right? When what I see here then that this is my omega critical, and when omega is less than omega critical, my theta equals 0, right? So I have this function. The theta of equilibrium position is 0, right? Remember that this one. But when my omega becomes larger than omega critical, the equilibrium position is given by this formula. And what I will have is a square root, like this. Okay? So that will be my total graph, like this. And that will be square root here, because it's cosine, it's square. And now what? But now let's now check the response. What if I somehow measure that equilibrium position, that theta equilibrium, as function of omega? I change omega a little bit, right? What it means? What does it mean? It means that I need to study the behavior of the following derivative. Right? This is how equilibrium position changes when I change omega. Right? By definition of derivative. Now this is my graph, right? So this is my response of equilibrium position to small changes of omega. But this is square root. What happens if I take the derivative of a square root?
You get like 1/2 under the 1/2 root usually.
I get 1 over square root. Let's forget about numbers, right? Yes, there is number factor of 2, of course, here. This 1 over square root. So this is that behavior is square root of omega minus omega critical, right? On this side. Here it's 0, here it's square root. When I differentiate it, I will get 1 over square root. So it will diverge. That behavior here, when omega larger than omega critical, is 1 divided by square root. Well, this some prefactors. Omega minus omega critical. So it's divergent, right? When omega equals omega critical, I divide by 0. So that means that this response of my equilibrium position to omega is divergent here. Right? So it means that my system responds very enthusiastically to small changes of omega. I change it by a little bit, and theta, bam, right? I multiply it by infinity. That's why noise is so important. So any little noise in my omega, like my motor has some noise. It's not keeping omega precisely. It never does, right? It has some error bar. But all those little noises in omega will be extremely important here because the response diverges. That's why close to those transitions, all those noises are so important. And that's exactly what we said at the beginning. It's when I squeeze that rod, like right, it goes to some direction by chance. That's exactly what it is. Any simple noise will lead to large response. Okay, that makes sense?
Yes.
All right, I have to stop here. Sorry again. And any questions? All right, that's it then. And I'll see you on office hours.